Hi, and welcome to 9.4 Conservation of Momentum Inelastic Collisions. In this lesson, students will be able to use the law of conservation of momentum to fully describe the motion of objects undergoing inelastic collisions. So, as a review, inelastic collisions occur when two objects collide and lock together. So, anytime you see a word problem where the two objects are coming and they stick together, it's inelastic. So it says, how can we rewrite the conservation of momentum formula in this situation? Pause the video and think about how would you rewrite this formula? Pause the video. How would you rewrite it? Well, you might say, okay, they're separate in the beginning, and then the two masses kind of add together and move with the same velocity. That's another hint. How would you rewrite that equation? All right, so this is the original one for inelastic collisions. Notice that since the masses are moving at the same velocity, we don't have to specify 1 and 2. It's the same thing. Oh, and if they're being multiplied by the same variable, then we could kind of take that variable out and put M1 and M2 in parentheses. So it's the combined masses moving together, moving at the same velocity. So if you're looking at this equation and you could see the collision in your mind because you understand that, you're doing good things. And look, for elastic, they bounce off each other, right? And they stay separate. All right, so that's what's happening there. And by the way, this is for perfectly inelastic collisions, where you have the maximum loss of kinetic energy and the objects do stick together. You could have a partially inelastic collision where they don't stick together, but you still lose some kinetic energy, so it's not considered to be totally elastic or inelastic. It's like a range in between. But for this class, they'll either be totally elastic and bounce off each other, or totally or perfectly inelastic and stick together like this, so we could use this new equation. Really, it's still just the momentum formula, where you have the initial momentum of the first thing plus the initial momentum of the second thing. And since they do lock together, we can consider the momentum of the two of them locked together, the mass times the velocity. You really just want to show that it's still just a conservation of momentum. The total initial momentum is equal to the total final momentum. The momentum does not change. It all boils back to this very simple formula. It looks more complicated, but even if you just have this on your reference table, given the situation, you should be able to make your own equation that looks like this. So let's do an example. It says a 1,200 kilogram car traveling at 25 meters per second east crashes head on into a 2,500 kilogram truck traveling at 15 meters per second west. The two cars lock together and slide across the road. They don't tell us if they slide to the east or west. I wonder which one is winning. Which one has more momentum? Does this have more momentum, the car, or does the truck have more momentum? That'll tell you which way they slide afterwards. So part A says, what is the velocity of the locked cars, or the car and truck? And what is the change in kinetic energy of the two-car system? All right, so let's take a look. We'll write the givens down. M1 is equal to 1,200 kilograms, and it's initially traveling with a velocity of 25 meters per second east, so that's positive. And then the second mass, the truck, is 2,500 kilograms. It's more massive, but it's moving slower. The initial velocity is 15 meters per second west, and we use the negative sign. Don't forget, if when you're reading these, maybe underline where you see west or left, just so you don't forget to make it negative. All right, so that's a tip. Underline it so you don't forget. It's easy to forget. Then it says, what is the velocity of the locked cars? Since they're locking together, there's only one final velocity, VF. We don't have to do V1F and V2F because they're moving with the same velocity. So what is that final velocity? Okay. Well, we can do the momentum, conservation of momentum. Okay, and initially they're separate. I'm writing it all out here. So the sum of the cars as they are approaching each other, and then after the collision, they're locked together, and that momentum is the same. So we have M1 V1I plus M2 V2I is equal to the combination of both masses as they're locked together, and we have the final velocity that we're looking for. Okay. Then we could plug in the numbers, so I'll do that. And we'll calculate, we'll actually do the initial momentum of the first car. The car is traveling east with 30,000 kilogram meters per second, plus the total, the vector sum of the momentums, right? Because these are vector quantities. Okay, the vector sum, meaning if this is traveling west, this is negative 37,500 kilogram meters per second. So to answer our question from before, like which direction are they going to slide across the road? All right, you could see the truck has more momentum, so they should be moving to the west. We should get a negative final velocity to indicate that they are going to move to the west because the truck had more momentum than the car, and that was traveling west. All right, so we added the masses together. When you add these two momentums together, the vector sum of the initial momentums is negative 7,500 kilogram meters per second. That is the total momentum for the two-car system. And we take the mass, 3,700 kilograms, times the velocity. See how that works out? This boils down to, it's going to look like our normal P equals mv equation. This is the total momentum of the system, and then this is the mass of the cars. What is the velocity of the cars? So you do the division, and you get a final velocity of negative, which is what we predicted, 2.027, 2.03 meters per second. All right, so they're not moving as fast as they were. They kind of like slow down to a stop because they just had a huge collision, right? So they're not moving as fast, but they are moving to the left, to the west, which is what we predicted because the truck had more momentum. All right, part B says, what is the change in the kinetic energy? So I'm going to write this over here. We know this is the final velocity. Okay. And I'm going to erase this other stuff so we have more room. All right, so since this is an inelastic collision and the cars lock together, we would expect there to be some change in kinetic energy. We would expect to lose some kinetic energy because that energy is transferred into other types of energy, such as internal energy, which is required to like deform the cars and the sound and everything else like that. So the change in the kinetic energy is equal to the final kinetic energy of the whole system together minus the initial kinetic energy of the whole system together. If this was an elastic collision, this would be the same magnitude as this, and delta Ke, the change in kinetic energy, would be 0 joules for elastic collisions. What we'll see is that the final kinetic energy is going to be, I'm predicting, less than the initial kinetic energy, and we're actually going to lose some kinetic energy, so there will be a change. All right, so how do you expand this out? Well, the change in the kinetic energy is equal to 1/2. It's going to be mv squared, right? But we're talking about the final. So this is like the total momentum times the final velocity squared. But we'll write it like this to stick with our subscripts that we have here. We have m1 plus m2. All right, so that's the final kinetic energy. The initial kinetic energy is the sum of 1/2 m1 v1I squared. So the car had some initial kinetic energy plus the kinetic energy of the truck, m2 v2I squared. All right. And not only is the velocity being squared so the negative number goes away, but remember, energy is a scalar quantity. This car has some kinetic energy. This car has some kinetic energy. You add them together, that's the total kinetic energy. This combination of cars also has some kinetic energy, but since it's inelastic, this is going to be less than the combined kinetic energy of these two initially. All right, so that's the basic idea. Now we have all our subscripts, and I'm just going to plug in the numbers. So that's what it looks like all plugged in. I'll simplify it a little bit. Okay, so this is the final energy of the system as the two locked cars move together very slowly. So you could see that's much less than each car individually. They're moving very fast and they're massive. This is a massive car and this is a massive truck, and there's a lot of kinetic energy in the beginning. And actually, hopefully this wasn't confusing. I forgot to put a plus sign there instead of a minus. You're adding the total kinetic energy together. This again, this is the initial kinetic energy of the system. That's all that's left over. This is the final. So what is the change in the kinetic energy? We get a negative number. We lost 648,626 joules of kinetic energy. Where did this energy go? Probably internal energy or heat. And the energy it causes, again, to deform all this metal. We have a lot of kinetic energy in the beginning, and then they slow down to almost to a halt. All right, so we're losing a lot of kinetic energy. It gets transferred into other types of energy. Cool stuff. So for inelastic collisions, you are losing kinetic energy, but the momentum is conserved, which is cool. All right, you could do this practice problem. Try this one out on your own. There's a couple tricks with this one. I'll read it to you and then do it on your own. It says satellite A has a mass of 2.5 times 10 to the third kilograms and is traveling east at 9.0 times 10 to the third meters per second. Satellite B is traveling west at 7.0 times 10 to the 3 meters per second. The satellites collide head on and come to rest. So that means they're moving towards each other and they collide. What is the mass of satellite B? Predict which satellite is more massive. Pause the video. Try it out. Okay, I'm going to try to make my prediction here. Okay. Which one is moving faster? Satellite A is moving faster, and they come to a rest, which tells me that the final momentum is 0. If the final momentum is 0, that means the initial momentum must be 0, which means when you add the momentum of A and B together, it's equal to 0, which means that they have the same momentum and moving in opposite directions. And since this one is traveling faster than this one, let's see, I think satellite B will be more massive than satellite A. It's going to be a greater number than 2.5. Let's see if I'm right. Okay, so the first step is to write the given information. Don't forget to make the velocity of B negative to show that they are moving in opposite directions. I said VB is moving to the west, and then they tell you it comes to a rest. So yeah, VF is equal to 0 meters per second. And if you wanted to, you could say, oh, well, I know the final momentum then is 0 meters per second. And that would help you with this step, because you could just plug in, okay, that's going to be 0. But I'll show the whole equation. And then since VF is 0, that's what I'm saying, that the final momentum is 0. and we will substitute in our values. Don't forget to make this negative, otherwise you'll probably get a negative number for your mass, which does not make sense. All right, so we'll simplify, rearrange the equation a little bit, and at this point we have the P is equal to mv equation, well, Vm, I guess, but yeah, this is the momentum, kilogram meter per second. This is the momentum of MAI. If you focus in on this, look at that. Oh, actually, it looks like this. Just this one here. Mission angle, nobody cares. Okay, yeah, but that's the momentum of A. The momentum of A is equal to 2.25 times 10 to the 7 kilogram meters per second. That's a lot of momentum. All right. And we know that it's equal to the momentum of satellite B. Here's satellite B over here. Let's see, all of this stuff is satellite B. How do we know that it's equal to B in this case? Because they come to a rest. So they have to be moving. A is moving this way, B is moving this way, and this momentum is 2.25 times 10 to the 7, and this momentum has to be negative 2.25 times 10 to the 7, because when you add them together, you want to get 0 kilogram meters per second. That, there's a little stuff going on in the background. It's not just about the equation. You should really know what the equation means, each individual term. So when you solve, you get the mass of B that's not a B, oh my gosh, is as predicted 3.2 times 10 to the third, or like 3,214 kilograms. Yep, that is the mass of satellite B, which as we predicted is greater than the mass of satellite A because it wasn't moving as fast, but we could tell it had the same momentum in the opposite direction because it comes to a rest. Anyway, that's about it. Thanks for watching and have a great day.